Greetings everyone. Welcome back into college algebra. Right now I want to take a sidestep from the new topics and we're going to talk about everything that's in this second unit of college algebra, typically what I give as a second test when I teach college algebra. One thing I want to remind you, and I know you hear this every time I do one of these, but it's a good thing to remember. Don't focus on individual problems. Make sure that you're letting the method and the general structure of what's going on sink in when we're working through these problems. Okay? Memorizing individual problems is a good way to say, I never saw one of those when you see something new on the test. When it's not actually new, you need to focus on the methods themselves, because problems don't always have to look alike to be the exact same type of problem. Okay, so go through these and make sure that you're seeing when I'm talking about the setup of all of these, not the specific problem itself. And while you're going through, remember, you can pause me and see if you can beat me to the answer. It's a good way to see if you're getting the actual skills themselves. This particular test covers everything to do with linear equations and functions, and just generic topic of functions itself. So linear equations in two variables is different than the linear equations from test 1. That was in one variable and that was solving. Linear equations in two variables is graphing lines. And along with that goes the system of linear equations goes with that. Okay? And of course, we wouldn't be able to graph them if we didn't talk about the Cartesian coordinate system. Distance between 2 points, midpoint between 2 points. Of course, that means you also need to be able to graph points and read location data on the rectangular Cartesian coordinate system. Circle equations come up from that also, being able to determine the equation of a circle, or if I give you the equation, be able to get the information in the graph. And then everything that we talk about on the generic topic of functions. So function algebra here covers everything about domain and range, whether it's from an equation or a graph. Reading graphs the same way, for domain and range, but also for intervals of increase and decrease and relative extreme points like relative maxes, relative mins. Graphing with transformations, being able to do all of the shifting, flipping, stretching techniques of graphing a function from a parent function. Okay, function notation, being able to understand whenever I have y equals f of x type of function setup. Difference quotient, being able to just find the formula for a difference quotient for a function. Combinations and composition, being able to plug a function into another one or add two functions together or such and so forth. Be able to find the inverse of a function, right? The opposite of a function. And then, of course, there's always piecewise functions as well. Functions that have to be defined mechanically and artificially. Okay? Let's begin with the expectations on linear equations of two variables. Of course, this stems out of all of the Cartesian system things, and I want you to also note that even though there were a bunch of skills listed, there may not be an individual problem for each of those skills. A lot of the skills are going to be built together, which is why a lot of the Cartesian point things are in the same kind of problem with the linear equations of two variables. Okay, you're going to find that a lot on math tests. They don't necessarily have to ask individual questions. Okay, so here, same thing. I'm going to be building from left to right here, starting with here. Calculate the distance between points A and B. Here's point A, and here's point B. Okay? We're supposed to be calculating the distance between them. So I'm going to use the distance formula between 2 points. Right? So distance is going to be equal to the square root of, and then I'm going to subtract the two x's. So that's 10 minus 4. And I'm going to square them. And I'm going to add the same idea with the y's. Negative 6 minus 7 and squared. And now I just need to simplify. So then this is going to be the square root of 10 minus 4 is 6 squared plus negative 13 squared. So that's 36 plus 169. So let's see, 35 and 70. I have the square root of 205. 205 is 41 times 5. So I can't factor this one into anything that can be reduced any which way. As far as answers go, this is a good place to stop, unless the question specifically asks for a decimal representation, in which case you could plug that into your calculator and then chop to the appropriate amount. Since this is an exact value and they didn't specify that, it's a good place to quit. Find the midpoint of C and B. So I've got point C and I've got point B, and I'm going to compute the midpoint of those two. So midpoint is going to be equal to, and remember I'm just averaging with these. So I'm going to average the x's. 4 plus negative 5 over 2. And I'm going to average the y's. 7 plus 2 divided by 2. So then what I end up with here is negative 1/2 and 9/2. Again, since it wasn't specified, this is a good place to quit. I don't have to necessarily put that into decimal or mixed format. Typically, I prefer to avoid mixed number format because it tends to clash with the way algebraic equations work. So improper fractions is fine for me. Some people may prefer the decimal if you're trying to locate it a little bit more accurately on a grid. It's whatever is called for. Next, create an equation for the line L. Now that's important that I've named the line. I've actually named a line L. You don't always see that in the algebraic stuff that we do. Okay, that's because we're going to reference that line later on. Okay, so keep that in mind. So I'm creating an equation for line L containing the points A and C. Alrighty, so I'm going to create the equation of a line using 2 points. Well, if I've got 2 points, that automatically right there can give me the slope of my line. And remember, when it comes to creating line equations, the most important piece of information that you can use with a line is the slope. So point A and point C, I'm going to compute their slope. The slope of my line, M, is going to be y minus y over x minus x. Okay, so point A, I've got negative 6 minus 2 over 10 minus negative 5. If you did it the other way where you put the 2 first and the negative 5 first, that's fine. We'll get the same answer. Okay, so I have negative 8 over 15, and that does not reduce. Okay, so I've got negative 8/15 as my slope. Now to create the equation of this line, I'm going to use point slope formula. Right, y minus y naught equals m, x minus x naught. And there's other forms of that equation too, but this one will most likely save us a little bit of time here. So I've got y minus y naught. And remember, in this spot right here, what I'm doing is I'm going to replace a point. So let's just use point A, for example. No, let's use point C. Sorry. The reason I picked that is because I always pick the one with the smaller numbers. It doesn't really matter which one you pick. Okay, in fact, I won't cross that out because you can pick either one. So that means y minus point C is 2. My slope is negative 8/15. And then x minus point C is negative 5, so plus 5. I'm going to distribute. Y minus 2 is equal to negative 8 over 15x minus, now 8 over 15 times 5 is 40 over 15, but that reduces, right, to 8 over 3. To finish up in slope-intercept, I'm going to add 2 to both sides. Now right here, instead of the number 2, I'm going to write something with a value of 2, which is 6/3. 6 divided by 3 does have a value of 2, but notice I now have a common denominator. Okay, so final slope-intercept form, y equals -8/15 x, and then I have minus 2/3 from here, right? This is -2/3. So here's the answer for that one. Unless it specifically says put it in, standard form or general form, whatever, in which case you can move the x over and multiply by whatever it takes to get rid of your fractions. You can do that too. It didn't specify, so I'm going to keep it in slope-intercept form as our favorite format. Okay, and lastly, we are asked to find the equation for the line perpendicular to L. There's line L. I need something perpendicular to L, but also needs to contain point B. Okay, so remember we just said a minute ago, the slope for line L, I'll do M sub L, that's what this is, M sub L here, was -8/15. So that means since we're going to be perpendicular, my slope this time, the slope of I'm using the perpendicular symbol here. I'm doing that so that you can see that I've changed it. Okay, you don't actually have to write it every time, but it is a good thing to keep informed whoever's going to read your paper. Remember, perpendicular means I'm going to do the opposite. So instead of negative, this will be positive. And I got to do the reciprocal. So 15/8 is the slope that I'll be using. And yet again, I will be using point slope form because that's the quickest way to create the equation of a line, especially given a point and a slope, right? I have point B and I've got this slope. Okay, so I've got y minus 7 is equal to 15/8 times x minus 4. Distribute. So I have y minus 7 is equal to 15/8 x minus, that's going to be 15/2 because 60/8 reduces. And then I'm going to add 7 to both sides. But remember, instead of adding the number 7 on this side, I'm going to add something that has the value, but has a common denominator. So I'll use 14/2. 14 divided by 2 is 7, but they have a common denominator here. And I'll be able to combine those two into -1/2. So final answer here, y equals 15/8 x minus 1/2. Next, let's begin our stroll into the function topics. List the domain for each of these 3 functions in equation form, and then reading the graph to give all of the different pieces of information that anyone could ever ask for at this time. Okay, so listing the domain for these 3 functions. Remember, what you have to look for at this point is just a few different things that could go wrong. Really, when you're listing the domain for something, what someone would be interested in is, where is this thing going to fail? What x values would blow this function up? Okay, so in this case, if you look at the top guy here, there are absolutely no problems like that. There's nothing that's going to cause a division by 0. There is a division, a fraction, but there's no variables in the denominator. There's no logarithms, there's no square roots, there's nothing else in there with any kind of domain issues. So the domain for this guy is all real numbers. So I could either use the double line R, or I could actually say -∞ to infinity. Okay? Next, I'm looking at this g of x here, and I'm seeing the denominator. The denominator on this one has a variable in it, and that's the big red flag. If I were to plug in either 5 or -5, it would cause a division by 0. So x cannot be plus or minus 5. And of course, that's one way to list the domain. Someone would say x can't be this. Typically, with functions like the way we're doing them here, though, we want to see a function notation of some sort. So in this case, if I have to cut out both 5 and -5, then my domain is going to be -infinity to -5, union -5 to 5, union 5 to infinity. And notice all of the pieces have parentheses because I'm not including any of the 5 or -5s, but anything in between, like to the left of -5, in between -5 and 5, or to the right of 5, right? That's what those intervals are listing there. Okay, and then the last guy here, the square root's big red flag is, of course, we don't want to square root negative values. So I would use the inequality 40 minus 8x has to be greater than or equal to 0. Whatever's inside the radical, square root can't be negative. So greater than or equal to 0 says non-negative. And then I proceed to solve for x. Dividing both sides by -8 reverses my inequality. And it tells me that x has got to be less than or equal to 5. This is one way to list the domain. But let's also give the interval notation. So here the domain is going to be everything from -infinity up to 5 with a bracket. Okay. Next, we're going to use the graph here to list out a lot of different skills that you need to be able to tell when you're looking at a graph. And it may seem like a lot of unrelated things, but all of these things tie together in your studying of graphs. Eventually, if you ever go on to do anything with calculus or with anything else that involves some sort of change in a function, or the graph is listing information over a whole of something, these are all things that businesses and scientists are all interested in graphs. Okay, let's start with the symmetry arguments, because I want to also talk about the symmetry over here in case those come up on a test too. Label the function as either even, odd, or neither. So I'm looking at the graph over here, and I've got to decide which one of these three categories it is. And remember, odd is whenever something is symmetric on the origin. I should be able to rotate it 180 degrees and get the same graph if it's odd. And that's not this one. Even is symmetric on the y-axis. So if you use the y-axis as a middle, is it the same on both the left and right sides? Yeah, this one is. It has exactly the same on each half right here. So this function is even, not odd, not neither. While we're on that same topic, I want to go ahead and throw out the labels on these. If you notice the exponents, 18, 10, 4, 2, and technically this is x to the 0. All of those are even powers and no restrictions on the domain. So this is an even function. Here I have an odd power, and here I have two evens. It's an odd divided by an even. Okay? Odd divided by even is going to give me an odd function. Anything with a square root in it has a domain restriction, which automatically throws out any kind of symmetry because it's a cut in half type of symmetry. So this is definitely neither even nor odd. Okay. Okay, next. Let's start listing out all of the properties of this guy here. Domain and range, I'm going to read directly off of here. So for the domain, I read from left to right. Do not let yourself go up and down. So from left to right, do I see any breaks? Nope. Nothing stopping, nothing breaking. So from left to right, it goes all the way left, it goes all the way right. My domain is going to be all real numbers. The range, from bottom to top. Nothing here, nothing here, nothing here. Look, oh, -2 is the bottom of those two. So my range starts with a bracket on -2. Then we keep going. Yes, 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 yes. Wait a minute. Approaches. Approaches. It never actually touches that line, but it gets infinitely close. Infinitesimally close, depending on which way you want to talk about it. So it goes up to 3, but parentheses on the 3 because it never actually meets it. Okay, now, intervals of increase, decrease, and constant. Remember, the trick for this one is to orient the graph. If I were drawing the graph from left to right, I would orient the graph in this direction. Like so. Like I'm putting little arrows on it, right? Okay, so orienting the graph, look at which way the arrows are pointing. Look, it's decreasing, it's decreasing, it's decreasing. The y value is going down until I get to this point right here. What x value is that point? That would be -2.5. Right here. Okay, so then it's decreasing from -infinity to -2.5. Next, it's increasing until it hits this center point. Don't put 2. It's the x value of 0 right here. So it's increasing from -2.5 to 0. All right, next. It's decreasing again until it hits this bottom point, and that bottom point, whoops, was supposed to be here. I'm going to fix the graph in the wrong color. Sorry about that. It was supposed to be at 2.5 because it's supposed to be an even function. It's got to be the same on both sides. Okay, so it's decreasing again from 0 to 2.5, and then from here on up it's increasing. So 2.5 to infinity. Constant. It's never a constant y value. So there are none. There are no intervals that are constant. Okay, extreme points. Okay, now before we were doing intervals, don't get those mixed up over here with points. They look the same when you're using the parentheses like this. The relative max occurs right here in the center. Notice these are not relative maxes because it never actually culminates at a point. Whereas right here I have this highest point in a little neighborhood. This point right here is at 0, 2. It's a relative max. Relative min. I've got 2 of them. Each of them occur at a bottom of -2, and I have it at -2.5 and +2.5. So -2.5, -2, and 2.5, -2. Intercepts. Anything that goes through an axis. Okay, so I've got x-intercepts here, 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 and here. And then I've got a y-intercept here. So I'm going to list the y-intercept first. That's 0, 2. Then I've got -3.5. I'm going to put plus and minus 3.5 just to save room. Comma 0. and plus and minus 1, comma 0. So there's actually 5 points there. I'm just listing the plus and minus to save space here. F of negative 3. This is function notation telling me look at the function when x is negative 3 and tell me what the y value is. The y value spot is blank. The output of the function is the y value. Okay? So at negative 3, here it is right here. Let's see. What is my y value? So at negative 3, looks like we're getting negative 1 for my y value. Okay, reverse. F of x equals 2. Well, that's telling me, look at the function f. I want to know what x value will give me an output of 2. In other words, a y value of 2. Don't forget, this is the y value. They want to know, hey, which x values will give out that y value of 2? Well, all right. Let's take a look. Y value of 2. Well, first of all, we have this one, right? X equals 0. That's 1. We have a couple more, don't we? Right here at 2. Try and keep it level here. You can see where it's hitting. Try to use the tip. Right here at 4.5. So 4.5. And of course, since this is an even function, you can tell it's the same thing over here at negative 4.5. Be sure that when you're looking at these graphs that you look for these kind of things. Like I was able to use the fact that it was an even function to help with the symmetry on all of these points. Things like of that nature. Let's continue talking about functions, and then we're going to throw in some more of the Cartesian coordinate stuff with circles. So find the function values for the function d of x is equal to 1 over x squared minus 16. I want you to find d of 0 and d of x equals 0. And these are actually things that should come up all the time. They're just not usually phrased the way that I have them written there. Here we're saying use the function d, and we're letting x be 0. Whenever x is 0, don't forget that's a y-intercept. So I'm asking this thing right here to find y-intercepts. And then right here, d of x equals 0. That's letting y be 0. Those are finding x-intercepts. Okay? So sometimes instead of writing out things in sentences, we actually have ways of symbolizing them with math symbols. Let's work these out. D of 0. This is going to be if I just plug in 0 for x. So that would be equal to 1 over 0 squared minus 16. But this is 1 divided by 0. So that's going to be undefined. Next, d of x equals 0. This is what's going to happen when I let y be 0. And the easiest way to imagine this is like substitution. Substitute in for d of x this function. So I'm letting this function 1 over x squared minus 16 equals 0. And then, of course, to solve this, what I'm going to do is I'm going to multiply by the common denominator here, which is x squared. So if I multiply by x squared here, here, and here, I'll reduce this to 1. This will be 16x squared. And 0 times anything is still 0. Okay, so then from here, I can solve this one directly. I'm going to add the 16x squared over. 1 equals 16x squared. And then I'll square root both sides. Square root of 1 is still 1, and the square root of 16x squared is 4x. Don't forget, since I introduced the square root in this step, should have a plus or minus. To finish up, I'll divide both sides by 4, and so I'm getting that x is going to be plus or minus 1/4 from that. So I found two x values, okay? Don't forget what that means. Here, for example, this means that d of 1/4 would equal 0. Also, same thing for negative 1/4. That's what we're actually finding here. Okay, next we have a piecewise function. And then we're asked to find the function values. So I've got these particular function values, p of -3, p of -1, p of 0, and p of 6. Here's my function p of x. Remember, a piecewise function is just a decision function. I just have to decide which piece. You do not give out multiple answers. Okay, I've seen this a bunch where people put multiple answers here. No, don't plug it into each one. You have to decide. Here it says x equals -3. Well, x equals -3 is not equal to 0, and it's not greater than 0, but -3 is less than -2. So I'll use it here. So I plug my x, -3, into this. That'll be 3 times -3 plus 7, which is -9 plus 7, which is -2. And there's that answer. -1. -1 is not less than -2, so I can't use the top one. -1 is not equal to 0. -1 is not greater than 0. -1 doesn't fall into any of those decisions. So that means I can't use any of the pieces. Technically what that means is -1 is not in the domain of the function p. So we'll just put undefined. Okay, next. When x equals 0, well, we have one that specifically says that. It says give out a 5 when that happens. Okay, so 5. And there's the answer for that one. And then p of 6. X equals 6. 6 is greater than 0. So I'll use this one. That will give me 4 minus 6 squared. That's 4 minus 36, which is -32. Right? So I've got my answers to that now. And that's the piecewise function. Now, list the center, radius, domain, and range, and graph. You can tell this is a circle equation because it has the x squared and y squared. But it's not in the nice, pretty format where I can just read the center and radius off. Okay, so this is what I'm going to do. I'm going to rearrange this using completing the square. Then I'm going to list out all the information and graph it. Okay, so to do that, I'm going to rewrite this x squared minus 6x. I'm going to leave a little gap, plus y squared plus 4y, gap, and I'm going to subtract the 9 to the other side. Then I continue my steps by putting the parentheses like so. I know that I have to have an x in a parentheses squared and a y in a parentheses squared, and I'm going to use both of these steps in conjunction to fill that out. Okay, so half of -6 is -3, and -3 squared is 9. If I add 9 to one side, I've got to add it to the other, plus 9 here. Next, half of 4 is 2. 2 squared is plus 4. If I add it here, I've got to add it here. Okay, then finishing up. -9 plus 9 is 0, plus 4 is 4. So this is the general form equation of a circle whose center is the point 3, -2. Remember, it's whatever zeroes them out. The radius is 2 squared. This is the radius squared here. So I have 2 as my radius. Okay? Now the domain and range I'll do after I've drawn the graph. Let's get the radius and the center drawn up there. I'm going to try and use a little trick to help me graph this thing appropriately. So my center should be at the point 3, -2, which is right here. And then, since the radius is 2, I'm going to count 2 in each of the cardinal directions. So I'll count 2 up, which would put me right on the axis. I'll count 2 down, which will put me at -4 on the y-axis. I'll count 2 to the left, which will be at the point 1, -2. And I'll count 2 to the right, which will be at 5, -2, right here. And then, of course, the circle is going to be all of the points that go around there. So let me see if I can use my trick here. I'm going to put this suction cup on the center. And then I'm going to get an appropriate amount of radius here. Pretty close. Whoops. There we go. We'll clean it up a little bit. I know on a paper, if you were doing this on a test, you wouldn't probably have that at your disposal, but maybe you would have an actual compass and a protractor and everything to bring with you if you had enough forewarning that you might be graphing a circle, right? Which if you studied, you probably would know. Okay, so let's finish up with the domain and range here, right? The domain of this circle is going to be from left to right. It starts at x equals 1 and stops at x equals 5. So 1 to 5 with brackets. And then the range from bottom to top, right? It goes from -4 to 0. So bracket -4, 0. These next two problems really don't have much to do with each other, but they are both in this unit together, and they happen to be next to each other on the test, and they fit both on the board really well. So I'll be working them here in the same scene. Solving a system of linear equations in 2 variables. I've got 19x plus 14y equals 80, and 8x minus 7y equals -5. Personally, I like elimination out of the multiple choices that we've talked about in this unit. We talked about graphing, we talked about substitution, and we talked about elimination. Elimination usually is the most efficient and usually avoids the most grueling, divisions and things like that. Because we're just using linear combinations, which means multiplication and addition. Okay, so here I'm noticing that I have a 14y and a -7y. So what I'm going to do is I'm going to multiply this bottom equation just by 2. The new resulting system is going to be 19x plus 14y equals 80 and 16x minus 14y is equal to -10. So then what I can do here is I can add up these 2 equations since they are completely lined up, and also these will add out to 0. That's going to give me a total of 35x is equal to 70. And of course, when I divide both sides by 35, I receive that x is equal to 2. And don't forget, to solve a system, I need a complete ordered pair. So I'm going to take this x equals 2, and I'm going to not do elimination again to save time. I'm going to cheat a little bit. It's not really cheating, but change methods. I'm going to go to substitution now. I'm going to take this x equals 2, and I'm going to plug it into one of the equations. I'm choosing the bottom equation just because of the smaller values. Okay, so then 8 times 2 minus 7y is then equal to negative 5. This is 16. So if I subtract 16 from both sides, I get that negative 7y is equal to negative 21. Dividing both sides by negative 7 gives me that y is equal to 3. So then I have the complete system solution there at 2, 3. Of course, to check this, I plug it into the other equation that I didn't use the substitution for as a double check there. 19 times 2 plus 14 times 3. 19 times 2 is 38. 14 times 3 is 42. 38 plus 42 is 80. So it does work out. This is actually the solution to that system of equations. Okay, next, we are given a function in function notation, and we're asked to do 3 main things here. Describe the transformations from the parent function version of itself, graph that function using those transformations, and then find the inverse and graph it also on the same grid. Okay, so let's start with the parent function and the transformations. The parent function here of this function is y equals x cubed. And remember, the original shape of y equals x cubed is the cubic swirly shape that goes through the origin like that. Okay, so I'm going to label the transformations here, and this is really the key. The reason why I word my test this way is a couple of reasons. One, I do want to see that you're able to graph it from the transformations, which is the important skill here. But also, describing them makes me see that you really are doing each individual piece correctly. And sometimes also, if there's a stretching in the graph, you can't always see it on the grid. But if you describe it in words, I know that you've seen it. Okay, so I ask all of my students to do both, to describe the transformations from the parent and then also to graph it. Okay, so let's go through the description here. It's obviously a cubic function. Right? It has been vertically reflected because of this negative in the front here. It's on the outside. The plus 4 is also on the outside, so it has been shifted up 4. And then lastly, the plus 2 here, it's been shifted left 2. So this is part of the answer right here. Excuse me. The cubic function part comes from the parent function, of course. And then all of the other things are the actual transformations. Okay, so then let's actually graph this thing. It started out being centered at 0, 0. If it's vertically reflected, right? Think about it. It's going this way normally. If it's been vertically reflected, that means this piece went up and this piece went down. So now I have this shape instead of the original. And then I'm going to go shifting the center point up 4 and left 2. So from the center, I'm shifting up 4 and then left 2 here. Okay, so let's use my handy dandy yardstick here. and I know you wouldn't always necessarily need to be this precise on your paper. I'm just trying to be as helpful as possible. Okay, and then from here, I'm just going to draw the cubic shape in. Now, here's the thing. How accurate am I? Okay, I don't know. The shape is correct, the location is correct, and the orientation is correct. When I myself go to grade one of these problems, that's what I'm looking for here. Because this particular method is not about being 100% accurate. It's about understanding what shape you should have, which direction it's facing, the orientation, and about where it's located. Okay? So in this case, we're spot on as far as all of those criteria. Now, does it exactly go through the axis here and here? I don't know. We would actually have to start plugging in numbers and solving things to figure that out. Okay? And that's not what we're interested in right now. I don't need precision. I just need a good generic structural understanding. And that's where we're at with that graph. Okay, find the inverse and graph it also. Well, finding the inverse is going to start off by letting p of x be represented with y instead. Negative, I have x plus 2 cubed plus 4. Okay, so then to actually do the inverse equation, I swap x and y. Or let me rephrase that. Everywhere there's an x, I replace it with y, and everywhere there's a y, I replace it with x. I'm not just physically swapping one for one here. Okay? Everywhere there's a y should appear an x, and vice versa. That is now technically the inverse, but it's just an inverse equation. I need to solve for y in order to get the inverse function. Okay, so then I'm going to start solving here. I'm going to subtract the 4. I'm going to divide both sides by a negative or multiply both sides by negative, whichever way you want to look at it. That technically gives me negative x plus 4. And then I've got y plus 2 cubed. In the next step, I'm going to reverse these to make it easier for me to write. You don't have to do that, though. Okay, the opposite of the cube power is the cube root. So I'm going to be doing the cube root, and I'm going to write this as 4 minus x. That's just a personal preference there. It's just easier for me to write as 4 minus x. You could still write negative x plus 4 if you'd like. Okay, and then in the last step, I'm going to want to subtract 2. Okay, so I'm getting here that y is equal to the cube root of 4 minus x. And then I have a minus 2 here. Okay? So then, to get the actual solution of finding the inverse, they mean a function. We've got everything lined up. I just need to write it properly now. P inverse of x is the proper name for this one. And it's equal to the cube root of 4 minus x minus 2. And that's the answer to that portion. Now, to graph this guy. There's a couple of ways you could approach this. Since I've already got the graph of the original, I could go with the graphing and inverse graph method, which would be to draw the line y equals x and then reflect this over it. Also, I can remember if things are inverses, they have all of their points reversed. So I can see that this center point here is at the coordinates negative 2, 4. That means the inverse should have the same type of center point at 4, negative 2. At 4, negative 2. Right here. Okay? And since I'm reflecting it across here, I should expect a shape where they actually hit each other, kind of like right here-ish. the line y equals x would be here, the two graphs should intersect here. So I'm sort of expecting this kind of thing right here. Like this. It's going to come out, it's going to swoosh down here. Because it's going to be the same shape, right? Now, the other way to do it is to do exactly like we did here. List out the transformations and the parent function, okay? If you look, the parent function is the cube root, right? And if you do y equals cube root of x, remember the original parent graph of that is this sideways cubic swirl. Okay, so we can go through some of the things here. You can see the -2 here means to shift down 2. Because 4 minus x is sort of reversed, you would think that a plus on the 4 would be a shift left. It's not. In this case, since the negative is on the x, it's reversed. It's actually a 4 shift to the right. Another way to prove this is if I plug 4 in, positive 4, 4 minus 4 is 0. Remember, whatever plugs in to make 0 on the inside of something like that is the original center's new location. So in that case, notice it would be 4, negative 2. 4, negative 2, as we speculated from the inverse here. Okay, so let's finish up. Obviously, there's a negative on the x, which would give me a horizontal reflection. So that means instead of going up at the top and down at the bottom, okay, it's going to go the other way. It's going to flip around this way and be up at the left and down at the right. It's going to do this way. Okay, well, that's all we needed to know. It's just like what I was saying here. It's going to come out from this way. It's going to go through, whoops, something like this. And obviously, like I said before, I'm like probably not very accurate here, but it's the generic shape, right? I need to have some sort of shape that's coming out this way and swooshing like a cubic like this. That's probably a bit better right there. Yeah. Okay? And then, of course, labeling the center point is important there. So those would be the two graphs that you should be looking for on this particular one. This last problem set finishes up all of the topics talking about functions in this unit. This is all of the advanced ideas of combining functions, but also the skill built in here is being able to read exactly what the function combinations are telling you to do and what is needed in order to move on into whatever functions you're studying. Okay, so here you're given 4 initial functions, w, k, d, and t, and then I have to do different combinations of the functions, and some of them have you actually plugging in values, whereas others are just finding a new function by combining 2 of the others. For example, t minus w of x. Do not say that this is t of x, t times x minus w times x. That's not what this is. T minus w of x. It just means that I'm going to take the t function, okay, 3x minus 2, and I'm going to subtract the w function, x squared minus 5x plus 6, like so. Okay, so I'm going to distribute this negative, which is going to give me negative x squared. And then I'm going to have plus 5x plus 3x, which is 8x. And then I've got negative 6 minus 2. So minus 8. This is t minus w of x. Next, it asks for dk of 9. Now remember, this is times, okay? Not to be confused with composition, which is the little circle. This is multiplication. So dk of 9. And there's a couple of ways you can do this. I could create the dk of x function and then plug in 9, or I can do d of 9 times k of 9. I'm choosing the latter. This is going to be d of 9 times k of 9. Okay? Since I'm not using the dk function for anything else in our circumstance, then it's easy enough to just do a couple of quick calculations and move on. If you were actually using the dk function for something bigger, and maybe you're researching whatever, then you'd want to create the function and then plug in 9. Here we don't need to do that. I'm just going to do d of 9, which is the square root of 9 minus 5, right, times k of 9, which is 7 times 9 over 9 plus 5. Okay, well, the square root of 9 minus 5 is the square root of 4, which is 2. And 7 times 9 is 63. 9 plus 5 is 14. Okay, well, let's see. 2 times 63 is 126, but 14 goes into 126 9 times. So this is actually equal to 9. Okay, another way you could reduce that, by the way, is this would be 2 over 14, which would give me a 7 in the denominator. 7 into 63 also gives you 9. Any which way you want to convert that one is fine. Okay, next, w over t of 0. It's important to check here that t is not going to zero out in this instance. If I plug 0 into t, I'm not getting 0, so we're good. Again, just like the last one, I could create the w over t function and then plug in 0. It actually won't be much different than what I'm about to do. I'm going to do w of 0 divided by t of 0. Okay? In this case, in these two cases, either way works just fine. Okay? Plugging in values on the compositions are the ones that you have to look out for, because you have to plug them in a staged, into one and then the answer into the next. But when they're just normal operations, you can split them. W of 0, 0 squared minus 5 times 0 plus 6 over 3 times 0 minus 2. So I've got 6 over negative 2, which is negative 3. Okay, now lastly, the composition of t with k, or k with t, whichever way you want to discuss that. Okay? This means that I'm taking the t of x function and I'm plugging it into the k function. So remember what that means is I'm going to write a generic k function, which is 7 times something divided by that same something plus 5. This is your k function. We write it with letters, to hold the place to plug stuff in, but this is actually what it means, right? I could put something in this spot. In this case, though, I'm not putting in a value. I'm putting in a whole function, t of x, 3x minus 2. Is what I'm plugging into the k function. Okay, so let's simplify that. In the numerator, I'm going to have 21x minus 14. And in the denominator, there's nothing to multiply. I can simply combine like terms here. I'm getting 3x plus 3 here. Okay, always helps to double check. Notice that I could actually factor this, right? I could factor this into 3 times x plus 1. And up here, remember our numerator was already factored before I distributed the 7. It has a 7 and a 3x minus 2. Notice nothing is going to reduce from that, so I'm not actually worried about doing that. This is just going to be my final answer, my final function there. Okay? So I hope me working through these problems helps you study for your test related to functions and linear equations of two variables in your algebra class.